Hello and welcome to Geology. I am Robert Lopez, and today I want to start Geologic Structures, which is Chapter 9. And one thing about geologic structures, many of them are related to mountain building. And so one of the words we'll learn about in this chapter is orogenesis, or the word orogeny. And the prefix oro in Greek means mountain, right? So, and then obviously genesis or geni means for the genesis or the origin of these mountain ranges. Now, one of the questions in the quiz deals with why are mountain ranges in these linear features, and the reason is because they parallel tectonic activity, and mountain ranges could occur at convergent margins like the Andes Mountains here, or the North American Cordillera. In fact, everything from basically Mexico here all the way up into Alaska is called the North American Cordillera. And Cordillera is a Spanish word which means mountain ranges, right? So that's the North American Cordillera. We have the Appalachians that are a linear belt, the Himalaya and the Alps up here, again, linear belt. So again, many of them dealing with convergent margins, but we do see some other linear ranges like in the East African Rift, where here we're seeing volcanoes and activity due to a tensional or divergent margin. And obviously we have the mid-oceanic ridges here, which are enormous mountain range features, but they happen to be underwater. So primarily convergent and divergent margins can give us these rifts or these linear mountain belts. Now, one of the key things about making these cracks and crumbles in mountain ranges is this idea of strain. And strain is a deformation. And really, I like to define it as a behavior of rocks to stress. And so here, this undeformed strata, as soon as some sort of tectonic stress, like compression or tension, it starts to work on these undeformed units, we're going to end up getting a deformed rock. We're going to have some sort of strain. And the deformation changes the character of the rocks, and usually it occurs in three ways. Your book mentions displacement, rotation, and distortion, right? So let's take a look at these. So the first one, displacement, is like a fault, right? So here, we've already talked about faults. This is where the hanging wall is moving down, so this would be a normal fault, right? The footwall is over here. And so it looks like, in this case, this older green schist has moved up. This being the hanging wall over here, a quartzite has moved down, right? So there's displacement is one. Sometimes I call that offset or slip, right? Slip or offset, but your book uses the word displacement. The other form is a rotation. And so in this case, tectonic tilting can result in a deformation. We no longer have the horizontal strata here, but there's some rotation and tilting there. And then finally, there is a distortion. And this is common to folds, right? So you can see these pretty tight folds that occur in here. Now, more on strain. Strain is a change in shape caused by deformation. And there are several types of strain. There's three fundamental types: brittle strain, ductile strain, and elastic strain. We've already talked about elastic strain, dealing with material snapping back to original shape after the stress has been relieved, right? For example, in the elastic rebound theory. In this chapter, we mostly are going to deal with the brittle and the ductile strain. So brittle strain is basically occurring with fracture, and usually this occurs where the rocks are still pretty hard, so then it's not going to happen very deep. It's going to happen above a region called the brittle ductile transition. So shallower levels in the crust, because once you get below that brittle ductile transition, the rock behaves like a plastic and starts to flow and experiences ductile strain, right? So other examples of strain are stretching. So here we're stretching this, and obviously we're not fracturing, so this would be a ductile stretching here, an elongation. There's also shortening. Usually we use the word for shortening for compression. In this case, we're not fracturing, so we must be deforming it in a ductile, kind of a plastic deformation. And then here, shear strain, right? Shear is sort of this forces acting in opposite directions, just like you would shear a deck of cards here, right? There's a slip going between the cards, so no longer a circle here. You have more of this ellipsoid here. And so what's happening here, the shear, we're deforming it, again, in a ductile deformation, but in two different directions. Now, going back to brittle, here's an example of brittle deformation. If we take a plate and we drop it, it's gonna fracture. That's an example of brittle deformation. Here's some rocks that are probably experiencing frost wedging, and so they've already have fractures in them. So you can see the fractures coming down the slope here. And what may cause brittle and ductile deformation depends on the temperature and pressure. So obviously, brittle will be at lower temperatures and pressures, higher crustal levels, whereas ductile deformation will occur where it's warmer, at deeper levels where there's more pressure and more temperature. And this one actually is an example of a ductile deformation. Here we have some dough, we put a book on it, it's going to sort of ooze out in this ductile deformation style. Here's a stretched pebble conglomerate right here, where the conglomerate pebbles have been stretched out, probably through ductile deformation, but there's probably also some pressure solution going on there, metamorphic process. Then in terms of stress, right, so we talked about strain. Strain is the behavior to stress. So stress is a tectonic force. And so a strain is a result of deformation, which is caused by this tectonic force acting on the rock. And then, and so the key thing is that stress is a force applied across a unit area. And here we have the same person, and here they're providing a force, but here it's an area over one can. But if you do it over several cans, you see that it's different. So there's a fundamental difference between a force and a stress. So stress has to deal with this area. So you have to, and think of it as the force of one tectonic plate working along an area of like the San Andreas fault zone, the 1,300 kilometers of fault zone, as it affects and grinds against a North American plate along that San Andreas fault zone, right? So it's a huge area. And so again, stress is a force over area. A Newton is the SI units for force, and it's basically a kilogram, so it's a weight. You probably are more familiar with PSI, pounds per square inch, so that's a stress. You're measuring 32 pounds per square inch in your car tire, right? So it's a force, in this case, pounds, acting along on the area of the sidewall of your tire, right? So what are the types of stress? We've gone over these a little bit with plate tectonics. There's shear stress. Again, that side-by-side movement common to transform plate tectonic boundaries. So note we deform the block here. So originally it's a nice square here. And as we apply the shear stress, we kind of make a parallelogram here by deforming it. Then for compression here, looks like we're squeezing greater in one direction and not as great in the other. So this block deforms due to the compression. So that's obviously typical of convergent margins. Here's a continent to continent convergent margin. And then the tensional stress, this third one, is we're pulling apart. And we pull apart here, we stretch out, we elongate. In fact, other words we talk about here, we elongate the crust. There's elongation here. Remember, there's shortening for the compression. Again, for this elongation or stretching, intentional environments would be at divergent margins or continental rifts. Then your book mentions this other one just about pressure, and they just call it pressure, but really the word is confining pressure, and that's pressure equal in all directions. Note that the arrows here are the same everywhere, so it's equal. So there's no change in the overall shape other than a compaction. So note that it gets smaller, but it's not distorted. For example, in these others, we see distortion, right? There's distortion going on in these two, and even in this one, but in this one, there's no distortion. There's just this compaction. So that's what we call confining pressure. In another video, I want to talk about this idea of strike and dip. Strike and dip is a universal symbol in geology, and it's this little symbol right here, and it indicates. We've already talked about strike. Strike is this horizontal line, and it's a compass direction. And so in reference to north. So the strike of this line is, in fact, if north, here's north going this way. So the strike is 40 degrees to the east of north. So I would say this is north 40 degrees east. That would be the strike. So we've talked about this already. Dip is always, by rule, perpendicular to strike. So dip will always be perpendicular to strike, 90 degrees away. But then dip, remember, it's the angle from the horizontal down to the geologic surface. So in this case, we're measuring these strata. They're all inclined. They're dipping, in this case, off to the east, off in this east direction. And we would need an inclinometer, a special compass that can measure this angle of dip. That's an inclinometer. So this, on a geologic map, we would see these strata here that are cropping out at the surface. But we would show this symbol on a flat two-dimensional surface for a map. We would see that it's striking north 40 degrees east. So remember, north is up this way. There's a north arrow. And it's 40 degrees toward the east, right? 40 degrees east. And then we see that it's dipping 30 degrees in this eastern or southeastern direction, right? Which is this direction here. So that's how we signify the structure of beds, right? Of geologic strata. We'll cover this more as we go along. Now, geologists use a special tool called a Brunton compass or a pocket transit. And the key thing about this compass, it's like many other compasses, but the key thing is it has a bullseye, so you can level your compass to get the correct needle towards magnetic north reading here. But it also has this other little inclinometer. This thing can kind of move around, so as you put it on the sloping surface to measure the dip, it can measure this dip angle. Sometimes people call it a plunge, right? So in fact, if we look at it here, the key thing about this geologic pocket transit or Brunton compass is that not only is it a compass, but it can measure angles, an inclinometer, to measure dip and plunge angles, right? So we can measure this dip angle, the angle from the horizontal, and then a plunge would be a line across a geologic surface here. So we'll mention those as we go along. Now, remember there are two fundamental fractures in rocks. One are faults, and faults have displacement or slip, right? Fractures with slip. But joints are fractures where there's no slip. This is over in Canyonlands region in Utah, over by Arches National Monument. You can see that the sandstones here, remember they were buried, compacted, and cemented, lithified, right? So they were under some pressure. Now that they're exposed to the surface, they're kind of relaxing and they expand, right? So these are, you think of these are almost like expansion joints. But the joints are fractures where there's been no slip, no slip. And then a vein would be where one of these joint fractures has been filled in by some secondary mineral, like a quartz vein or a calcite vein. So these veins, fractures filled with new minerals, right? Those are called veins.